Welcome back. This will be the second part of a video lecture on section 3.3, the inverse of a matrix. In our first part, we looked at what is an inverse and properties of invertible matrices. In this second part, we'll pick up where we left off and look at elementary matrices, the fundamental theorem, and finally, computing the inverse. So let's begin with elementary matrices. An elementary matrix is any matrix that can be obtained by performing an elementary row operation on an identity matrix. And by this we mean a single elementary row operation on an identity matrix. So for example, here's a type 1 operation. I'm going to take the 3 by 3 identity matrix and I'm going to switch row 1 and row 2. This matrix here on the right is an example of an elementary matrix. Here's an example of a type 2 operation. I'm scaling row 3 by a factor of 2. And you can see that this matrix here on the right is an example of an elementary matrix. Finally, here's a type 3 operation. In this case, I'm going to take the identity matrix, I'm going to scale row 2 by a negative 3, and I'm going to add that onto row 1. So the result here on the right is an example of an elementary matrix. Our next theorem, Theorem 3.10, contains a very important property of the elementary matrices. Let E be the elementary matrix obtained by performing an elementary row operation on an n by n identity matrix. If the same elementary row operation is performed on an n by r matrix A, the result is the same as the matrix E times A. To put it another way, multiplying on the left by an elementary matrix has the same effect on the matrix A as performing the underlying elementary row operation. So we can perform elementary row operations in effect by multiplication on the left by an appropriate elementary matrix. Now let's explore the meaning of this theorem by looking at a concrete problem. So let A be the matrix that's given here. First, perform the row operation negative 3 times row 2 added onto row 1 on the matrix A. And then 2, show that this same row operation can be affected by left multiplication by a corresponding elementary matrix. So join me at the document camera and we'll take a look at this problem. All right, welcome to the document camera. Our goal here is to first perform this row operation on this matrix A. So let's carry out this row operation. We have to take negative 3 times the second row and add that on to the first row. So let's see, the second row is not going to change. We'll write that in as 1, 2. Now I'm multiplying by negative 3. I'm adding up, so that's going to give me a negative 7. I'm multiplying by negative 3, so that's a negative 6 added onto the 3 is going to give me a negative 3. Now what Theorem 3.10 is telling us is that we can affect this same change by doing a multiplication on the left side of A by an appropriate elementary matrix. And that elementary matrix is the one I obtained by doing this same row step on the identity matrix. So if I do that, I'm going to get the elementary matrix E that has that second row, but then I've affected this by multiplying that row by negative 3 and adding up. So I'm going to end up with 1 and negative 3. So there's the elementary matrix that should have, according to Theorem 3.10, the same effect as this row step. Let's check this out. So this is according to Theorem 10. I should be able to take the matrix E multiplied by the matrix A on the left, and this should produce the same thing as the row step itself. Let's find out. So when I do the multiplication, I'll have negative 4 plus negative 3, that's the negative 7. I'm going to have 3 minus 6, 0, 1, 0, 2. and those are equal to each other. And that's what theorem 3.10 is saying, is that a row step can be affected, we can create the same effect on a matrix by multiplication on the left by the elementary matrix of the same type. Okay, let's head back to the class notes and continue. Our next theorem, theorem 3.11, contains another important fact about elementary matrices. Each elementary matrix is invertible, and its inverse is an elementary matrix of the same type. Let's go to the document camera and explore the meaning of theorem 3.11. Welcome to the document camera. I'm not going to give you a full proof of theorem 3.11. Instead, I will show you enough to indicate the direction of a complete proof. I think this will help us see more what's going on if we kind of concentrate on something a little more concrete than a full proof, but it'll be enough to point in the right direction. So here's the idea. Let's imagine that I start with the identity matrix and I perform some row operation on it. Let's say I take -3 times row 2 and I add that onto row 1. Now that's going to take me to a matrix, let's call it E, which is an elementary matrix because it's obtained by applying a single row operation to the identity matrix, and so that's going to carry us to some elementary matrix E. Now, every row operation has another row operation of the same type that will immediately undo it. In other words, if I apply that row operation right after this one, it'll undo it. And for this kind of type 3 operation, we know exactly what to do. We just have to change the sign of that scalar. So if I immediately apply the row operation 3 times row 2, add it onto row 1, that's going to undo this previous one, and it's going to take us back to the identity. All right, now, this is where things can get a little strange, but let's think about what's going on here. We now know that a row operation, right, the change that a row operation brings about can be affected by the multiplication by an elementary matrix on the given matrix on the left. Now, what is the elementary matrix that affects this change? It's the elementary matrix I get by applying this operation to the identity matrix. But we already have a name for that. That's called E. So above this row operation, I'm going to write the matrix E, indicating that multiplication by E on the left has the same effect as this row step. All right, now let's think about this one. This is another elementary operation. If I applied this to the identity matrix, I would produce a matrix, let's call it E prime. And multiplication by E prime on the left would have this same effect. Okay, let's call this chain 1. We've chained together some matrices. We've produced some equivalences using row operations, or we can think about them as being affected by matrix multiplication. All right, let's produce another chain now. Now I want to start with the identity matrix, and I want to do this row operation first. Now, where's that going to take me? Well, let's look at the meaning of E prime. E prime is the matrix that I get. It's the elementary matrix that I get by performing this row operation on the identity matrix. But that's exactly what I'm doing here. So of necessity, this row operation is going to take I to E prime. And now I'm going to undo this. I'm going to undo this row operation by performing this row operation. And that's going to take me back to the identity. Now above each of these, let's write the matrices that have the same effect through multiplication. So this is going to be E prime. And this is going to be E. All right. Now here's what I want to do. We thought of this chain as being produced by row operations, and we thought of this chain as being produced by row operations. What I want to do is write out equivalence statements Let's call it 1 prime and 2 prime. Now thinking about this chain as being produced by matrix multiplication. So we're starting with I, then we're multiplying by E, and then we're multiplying that result by E prime. So I'm always multiplying on the left. And what our theorem tells us is that that's going to take us through this chain. It's going to take us from I to E to I. So I should end up at the identity matrix again. Now let's reinterpret this statement. This will be 2 prime. I'm going to start with the identity. I'm going to multiply by E prime. And then I'm going to multiply by E. And that's going to take me to the identity. All right, so this chain interpreted as row operations can be reinterpreted as matrix multiplication, and this chain can be reinterpreted as matrix multiplication. Now let's think about what we have here. I'll call this 1 prime prime. We'll reinterpret this now. Let's lift up the parentheses and reassociate. So this will be E prime times E multiplied by I. Equals I. And when I reinterpret this one, I'll lift up the parentheses, reassociate. That's also equal to I. But multiplication by I leaves this matrix unchanged. So statement 1 double prime is really saying E prime times E is equal to the identity. And statement 2 prime prime, again multiplying by I, leaves this unchanged. So this is saying E times E prime is also equal to the identity. Now when we put these two statements together, what do we learn? We learn that for this elementary matrix, I can find another elementary matrix E prime, and it's very easy to see how to get that. I just have to find the elementary row operation that undoes the one that we started with. So if you give me an elementary matrix, I'll think about the row operation that's associated with it. I'll think about the row operation that undoes it. I'll form this companion matrix E prime. And what property does it have? When I multiply E by E prime on the left, I get the identity. And when I multiply E by E prime on the right, I get the identity. And that says two things. First, E is invertible. Right? That's the test of invertibility. Can I find a matrix that operates in this fashion? And it also tells us that the inverse of the matrix E is this matrix E prime. In other words, it's easy to think about what the inverse of this matrix E is going to be. Find the companion matrix E prime by undoing the row operation and finding the corresponding matrix, and that will be the inverse matrix of your elementary matrix. Okay, so that's not a full-blown proof of theorem 3.11, but you could easily see how to adapt this to any row operation. We picked on a type 3 operation. This could be a row switch. It could be a pure scaling. Any substitution that you would want to make in terms of the type of row operation that's handled here is going to produce essentially the same proof. So this is not a full-blown proof of theorem 3.11, but it's pointing you in the right direction. All right, let's head back to the class notes. Let's put some of this theory to use. Let's take a look at the following problem. So let A be the matrix that's given here. And I want us to observe that by performing the following sequence of row operations, we can reduce the matrix A to the 2x2 identity matrix. So part 1 of the problem says, find elementary matrices E1, E2, and E3 such that multiplication on the left of A by E1, then E2, and then E3 produces the identity matrix. In step 2, we want to show that A can be expressed as a product of elementary matrices. And then finally, in part 3, I want us to show that the inverse of A can be expressed as a product of the elementary matrices E3, E2, and E1. So join me at the document camera for the solution to parts 1, 2, and 3 of this problem. Welcome to the document camera. We're going to work this problem. And in this problem, we have a matrix A that is being row reduced to the identity in 3 steps. 3 row operations take the matrix A to the identity matrix. And in part 1, we're trying to show that there are 3 elementary matrices, E1, E2, and E3, whose product in this order with A produces the identity matrix. Now, what we know is that there's going to be an elementary matrix that has this effect by multiplication on the left. So let's think of this as there's an elementary matrix associated with this row operation. Let's call this matrix E1. We'll call this matrix E2, and we'll call this matrix E3, or the corresponding matrix. So we'll call those E1, E2, and E3. Now let's identify those matrices. We can write them out quite literally. Remember that all we have to do is apply this row operation to the identity matrix, and that's what's going to identify E1. So E1 is what we get when we take the identity matrix, take -1 times row 1, and tack that onto row 2. So row 1 is going to be fixed, and row 2 is going to change according to this recipe. So I'll get a -1 in this position, and I'll have the 1 in that position still. So that's E1. E2 is going to correspond to applying that row operation to the identity. So we're scaling row 2 by 1/2. So row 1 is the same, but row 2 changes by that scaling. And then finally, E3 is going to be what obtains from taking the identity matrix and applying this step. So we're taking a -2 times the second row and tacking it onto the first row. So the second row is the same, and the first row changes by taking -2 times this and adding up. So we'll have the -2 in this position, and we'll still have the 1 in that position. Okay, so according to our theory, the theory being that there's an elementary matrix that affects this row change or this row operation by multiplication on the left, what we've shown is that if I take the matrix A and apply E1, that's going to take me from here to here. And then if I apply E2, I'm going to go from there to there. And then if I apply E3, I'll go from that matrix to that matrix. And that means that this multiplication will produce the identity matrix. And that's what we wanted to show in this first part. Okay? Now, as we're approaching part 2, let me remind you about something about elementary matrices, right? All of these elementary matrices are invertible, and that means in particular that their product is invertible. Okay? So this product E3 times E2 times E1 is itself invertible. So by multiplying by its inverse on both sides on the left, I can clear this from this left-hand side and put its inverse on the right-hand side. So let's do that. So I'm going to take E3, E2, E1 inverse times E3, E2, E1 times A. And on this side, I'll have E3, E2, E1 inverse times the identity matrix. So let's talk about this one more time before we continue. Because each of the elementary matrices is invertible, their product is invertible. That's a property of invertible matrices. So the product, this item that I have in parentheses here, is itself an invertible matrix. And so I'm just using that symbol temporarily to stand for the inverse of that product. I multiply that inverse on both sides on the left in this matrix equation. This product will give me the identity matrix. So I'll have the identity matrix times A on this side. And on this side, I'll just have E3, E2, E1 inverse, because multiplication by the identity will leave it unchanged. Okay, now this side is going to become A, because the identity times A is just A. And let me pull out one more fact about the inverse of a product of matrices. I can apply the inverse to the parts provided I reverse the order of multiplication. So I can render this as E1 inverse, E2 inverse times E3 inverse. And then there's just one last thing we have to remember, is that the inverse of an elementary matrix is itself an elementary matrix. So each one of these is an elementary matrix, and therefore A can be expressed as a product of elementary matrices. That's what we've shown. Okay, so let me just say that one more time. Each elementary matrix has an inverse, which is itself an elementary matrix. So when we're looking at this, that's an elementary matrix, that's an elementary matrix, and that's an elementary matrix. And so A is expressed as a product of elementary matrices. Great. The last thing we have to show is that A inverse equals E3 times E2 times E1. Now, what do we know? We know that A is a product of elementary matrices, and that means it's a product of invertible matrices. And this in particular says that A is invertible. Okay? A has an inverse because it's being represented as a product of invertible matrices. And in fact, A inverse is equal to E1 inverse times E2 inverse times E3 inverse inverse, right? If A is equal to this, its inverse is the inverse of this. And now I'm going to use my inverse rule on products once again. I can apply the inverse to the parts, provided I reverse the order of multiplication. And so this is E3 inverse inverse, E2 inverse inverse, and E1 inverse inverse. Okay. Now the inverse of the inverse is the matrix itself. So this is just E3. This is just E2. And this is just E1. So the inverse of A is just that product of elementary matrices that we see here. All right, and that's our proof. Now, if we step back and look at what we've done, we can abstract out of this something a little more general, right? What is it that's driving this problem, right? It's the fact that our matrix A can be row reduced to the identity, right? Once we have that, this whole chain, this whole argument proceeds just as it did in this particular case, right? So let's think about that. Let's try to pull out a more general principle if we can. So let's say we have a matrix that through a series of row operations, let's say k row operations, takes us to the identity, all right? So maybe there are k row operations, okay? In this case, there were 3, but there could be any number of row operations that are required. But let's say we can do that. We can get from A to the identity in k row operations. Well, we're going to be able to prove something like this. Just as we did here, we can identify every one of those row operations, and we'll be able to show that there's going to be a sequence of elementary matrices that will multiply A on the left in this fashion. That will take it to the identity. And then we'll be able to leverage that to show that since these are elementary matrices, they're all invertible, right? Therefore, their product is invertible, and we'll be able to show that A, just as we did here, A will be expressible as A1 inverse times A2 inverse on out to EK, E1 inverse, E2 inverse up to EK inverse. And then finally, we'll be able to do this last step and show that the A is invertible and its inverse is going to be EK times EK minus 1 on down to E1. So all of this hinges on being able to row reduce A to the identity matrix. Once we have that in place, it really doesn't matter if there are 3 steps on a 2x2 matrix or k steps on an n×n matrix. We'll be able to prove things that are equivalent to 1, 2, and 3 in general. All right, so there was nothing special about this matrix and these three particular row operations. This is an argument that's extendable. All right. Okay, let's head back to the class notes and continue. We are now ready to state and prove Theorem 3.12, the fundamental theorem of invertible matrices, version 1. Let A be an n by n matrix. The following statements are equivalent, and there are 5 statements A through E. So A, the matrix A is invertible. B, the system of equations AX equals B has a unique solution for every column vector B in Rn. Statement C, the homogeneous equation AX equals 0 has only the trivial solution. Statement D, the reduced row echelon form of A is the identity matrix. And finally, statement E, A is a product of elementary matrices. Now, every one of these statements, A through E, feels a little different than the others. They're all saying something different about the matrix A. But the theorem is telling us is that they're all bound together. There's like a giant wheel of statements, and they're all bound together. Once we know that one of them is true, we know that all of them are true. All right, welcome to the document camera. Let's look at the proof of Theorem 3.12, the fundamental theorem of invertible matrices. This is version 1. Now we have to show that these 5 statements, A through E, are equivalent. And technically what that means is that if I knew that any one of them is true, then they would all be true. All right. Now, one way of doing this, and this is kind of the classical way of doing this, whenever you want to show that some set of statements are equivalent, is you can think of arranging them on a cycle. So in this case, A to B to C to D to E to A. And then what we're going to show is that if A is true, then B is true. And that if B is true, then C is true. And if C is true, then D is true. And if D is true, then E is true. And if if E is true, then A is true. So we're going to show 5 implications. A implies B, B implies C, C implies D, D implies E, and E implies A. If we can show this, then no matter which of these 5 is found to be true. So for example, if we find that C is true, then by working our way around the cycle, we can see that we can tip the rest of these dominoes. So C would imply D, would imply E, would imply A, would imply B. So the truth of any one of these things would imply the truth of the others. All right, now let's begin. Let's begin with A implies B. Let's think about that. Now this one's particularly easy because Statement A says that A is invertible, and we know from Theorem 3.7 that when A is invertible, then AX equals B has a unique solution for every B in Rn. That is just Theorem 3.7. So A implies B, and this is just the content of a previous theorem, Theorem 3.7. So we can check that one off. We've already done the work for A implies B. Now let's look at B implies C. Okay, let's see if we can form this next chain. B implies C. Now, what do we know from B? We're saying that B is true. So we know that AX equals B has a unique solution for every B in Rn. And C asks us to show that AX equals 0 has only the trivial solution. So all we have to do is something like this. We could say, consider the equation AX equals 0. We know that there's one solution, namely the 0 vector. So x equals 0 is, we would say, a solution. But by B, this solution is unique. That's what B is telling us. It says, if you can find a solution to this equation, it must be unique. So, but by B, this solution is unique. Therefore, x equals 0 is the only solution. Okay? And that's what statement C is asking us to show that the only solution to that homogeneous equation is the zero solution. Okay, let's go to C implies D. Now, so we're assuming that ax equals 0 has only the trivial solution. That's what we're assuming in our implication C implies D. And what we want to show is that this implies that the reduced row echelon form of A is the identity matrix. Now, one way of thinking about this, one way of getting into this is to think about the context for a reduced row echelon form. So let's imagine that we're trying to solve the equation ax equals 0 by elimination. All right, now remember that C is telling us that there is only one solution to this system, namely x equals 0. But let's think about how we would find solutions to this homogeneous system. So one way of thinking about this is to look at this augmented matrix, where I take the matrix of coefficients and I augment it with this column of zeros. Then we would do row steps. Until we had A in its reduced row echelon form. Now, I'm not going to make any assumptions about what that form looks like. I'm just going to call it A star. This just works in general. I can always take this matrix A and do a sequence of elementary row operations to bring it into its reduced row echelon form. So this is the reduced row echelon form of A. Now, if you remember, how do we think about solutions to this system or this system once we have it in reduced row echelon form? Well, we would look at all the different columns, right? That would correspond to all the different variables. In this case, it's an n by n matrix, so there are n variables associated with the n columns. If any one of those variables didn't have a leading one, there would be a free variable, right? And if there were a free variable, there would be infinitely many solutions. But we're being told that ax equals 0 has only one solution. This system can only have one solution. And that means that there can be no free variables. So since ax equals 0 has a unique solution, there are no free variables. And what does that mean? It means that every column contains a leading one. Okay? But the number of columns and the number of rows are equal because our matrix is square. So every column contains a leading one. Every row contains a leading one, and that forces A star to be the n by n identity matrix. Okay? And that's what we were trying to show in part D. So the uniqueness of this solution to this homogeneous equation is completely equivalent to this row-reduced echelon form of A being the n by n identity matrix. Now, I've prepped you for D implies E by the previous problem we worked on. So let's just see how we can leverage what we've already done in a previous problem to help us with D implies E. Okay, now we're assuming that D is true. We're assuming that we can take the matrix A and perform a sequence of row operations to transform A into the identity matrix. That's what the truth of D is. Now, I showed you in that previous problem that anytime we can take our matrix and transform it into the identity matrix through a sequence of elementary row operations, that's equivalent to saying that I can take A and multiply it by a sequence of elementary matrices that takes it to the identity matrix, right? I can transform each of the row steps into an equivalent elementary matrix, and I can get the same effect by left multiplication by a sequence of elementary matrices. Now we know that the elementary matrices are all invertible, and so I can rewrite A as E1 inverse, E2 inverse, EK inverse. And the last piece that we have to see to finish the part the D implies E is to notice that E1 inverse is itself an elementary matrix. E2 inverse is an elementary matrix, and EK inverse is an elementary matrix. And so this is, in fact, a product of elementary matrices. Okay, so this is just like that problem we just worked. All right, so D implies E. And then finally, we have to show that E implies A. So we're assuming E. We're assuming that A is a product of elementary matrices. Now, that means that A, in fact, is a product of invertible matrices. And we know that a product of invertible matrices is itself invertible. And so we know that just by virtue of being a product of elementary matrices, it's a product of invertible matrices, and therefore A is invertible by properties of invertible matrices. So we can easily get from E to A just by making that observation. Okay, so that draws our proof to an end because we've shown this chain of implications: A to B, B to C, C to D, D to E, and E to A. And now we have this wonderful fundamental theorem of invertible matrices, version 1. And what it's really doing is it's linking together in a very nice way many of the elements of the things that we've been talking about in this course: solutions to systems of equations, homogeneous equations, non-homogeneous equations, facts about invertible matrices, row reduction to a row-reduced echelon form, etc. So it's a really nice kind of capstone result that brings a lot of the things that we've been studying together. So it's a fantastic result. Now, it's one that you can spend a lot of time thinking about. So I would encourage you to just kind of think about how all of these 5 statements are intimately connected with each other. All right, let's head back to the course notes. Here's theorem 3.13. Let A be a square matrix if B is a square matrix such that either A times B is equal to the identity, or B times A is equal to the identity, then A is invertible and B equals A inverse. Now let's put this result into context. If I wanted to show that A was invertible, I had to show the existence of a matrix B such that when I multiplied on the right by B and I multiplied on the left by B, I got the identity matrix. What theorem 3.13 is saying is that if I want to show that A is invertible, all I have to do is produce a matrix B that either multiplies on the right to give the identity or multiplies on the left to give the identity. One of those two would suffice. In fact, I don't have to show that both of them are true, because what this theorem is saying is that as soon as one of them is true, the other one must be true as well. So this greatly simplifies the situation for us. If I want to test the invertibility of a matrix A, I merely have to show that there's a matrix that multiplies on the right to produce the identity, or I have to show that there's a matrix that multiplies on the left to produce the identity, but I won't have to show both of them. They will both be true by showing that one of them is true. All right, let's go take a look at the proof of theorem 3.13 at the document camera. All right, welcome to the document camera. We're going to look at the proof of theorem 3.13. And in this theorem, in the statement of this theorem, the matrix A has been given to us. It's a square matrix. And somehow a matrix B has been found that has either this property, that when I multiply on the left with A, I get the identity, or it has this property that when I multiply on the right of A, I get the identity. What we have to show is that if this is true, or if this is true of the matrix B, then B must be the inverse of A. All right, now, how are we going to do this? We're going to treat these as separate cases. I'll prove this case for you, and I'll leave this case for you to do as an exercise. So let's take a look at this case. What we want to do is we want to imagine looking at any possible solution to a homogeneous equation. So I want to let x be any vector satisfying the homogeneous equation ax equals 0. Now we always know that there's one vector that satisfies this equation, namely the vector consisting of all zeros. So the so-called trivial solution is always a possible solution to this. But in this opening move in this proof, I want to just assume that x is any vector satisfying this equation, that ax equals 0. Now what I can do is use the fact that if I multiply on the left by b, that I turn b times a becomes the identity. So let me show you how we can use that fact. Let's multiply on the left on both sides of this equation by the matrix B. Okay, now I can use association and write this as b times a times x. And on this side, when I take the matrix B and I multiply it by this column of zeros, that's going to multiply to the 0 vector again. Okay, just think of that as a column of zeros here. And we know that b times a is equal to the identity, so this is just the identity times x. And the identity times x is just x. And so what we've shown that is if I assume that x is any solution to this homogeneous equation, then it must be the 0 solution. That means that the 0 solution, the trivial solution, is the only solution. Now, if we think about what that means, right, that gets us into the stream of theorem 3.12, right? And that says that one of the consequences of this is in other words, if the trivial solution is the only solution to this homogeneous equation, this implies that A is invertible. So our fundamental theorem of invertible matrices, version 1, comes to the fore here. By theorem 3.12, A is invertible. Now remember, we're trying to show something about the matrix B. We've discovered something very interesting about the matrix A, that it's invertible. But we're trying to show something about the matrix B, so we're not quite done yet. Now what I want to do is I want to multiply this basic equation here by A inverse on the right. Okay, and I'll just do the usual reassociation. Okay, A times A inverse is the identity matrix, and B times the identity matrix is just B. And that's the conclusion we wanted to draw, that if this matrix B exists, it must be the inverse matrix. It must be the inverse of A. Okay, so that's our proof for theorem 3.13 or theorem 3.13 in the case where I assume that B multiplies on the left to produce the identity. Now I want you, as part of your homework, to try to imitate this proof. You'll have to make some changes. You can kind of imitate the formal structure of this proof, but you'll have to make a few changes and try to show that if I multiply on the right by B, if that multiplication produces the identity, then B is also the inverse of A. Okay, so that's the proof of theorem 3.13. It's a beautiful proof. I hope you enjoyed it, and it shows how our fundamental theorem is coming to the fore in a big way here. All right, let's head back to the class notes. Here's theorem 3.14. Let A be a square matrix if a sequence of elementary row operations transforms the matrix A to the identity matrix, then the same sequence of elementary row operations transforms the identity into the inverse of A. So in other words, let's think of it this way. Suppose that I have a sequence of elementary row operations. Let's think of it as a row operation recipe, and that row operation recipe takes the matrix A down to the identity matrix. What this theorem is asserting is this. It says if I start with the identity matrix instead and perform that same row operation recipe on the identity matrix, that I will end up at the inverse of A. All right, let's go take a look at the proof of theorem 3.14 at the document camera. Welcome to the document camera. Let's look at the proof of theorem 3.14. We've got a square matrix A that has been reduced to the identity matrix through, let's say, k row operations. Now we know that we can think of row operations as being affected by some elementary matrices. So this is equivalent to saying that there's a set of k elementary matrices, one for each of these row operations, that slowly transforms through matrix multiplication the matrix A into the identity matrix. So we're effectively saying this. Each row operation can be done by multiplication on the left by an elementary matrix, and so we can think of this product of elementary matrices on the left producing this effect. We're going to get the identity matrix. Now, we know that this collection of elementary matrices is the inverse of A. One way of thinking about this is just to think that it's a matrix that multiplies A on the left and gives us the identity. So that must be, according to our previous result, this must be the inverse of A. So we can write A inverse is equal to EK times EK minus 1 on down to E2 times E1. And let's do one last step to seal the deal. This is it looks like a trivial step, but it'll help us visualize the conclusion. I'm going to tack on the identity matrix at the end. And the reason I want to do that is because now this looks like a row operation, right? It says, if I start with the identity matrix and perform the associated sequence of row operations, E1 through EK, I will result in the inverse matrix, A inverse. So these same K row operations performed in exactly the same order, starting with the identity matrix, will result in the inverse matrix of A. So A followed by the exact same K row operations in exactly the same order will result in the inverse matrix. And so that's what theorem 3.14 is telling us, and we can use this to great effect, as we'll see. Our theorem 3.14 gives us an excellent method for computing the inverse of an invertible matrix. So let A be an invertible matrix. The inverse of A can be computed via Gauss-Jordan elimination, and we're going to use the following scheme. We're going to take our matrix A and we're going to augment it by a full identity matrix. So this will now be a large rectangular matrix, two square matrices next to each other, the matrix A and the identity matrix of the same size. Now our goal is to do a sequence of elementary row operations with the intention of turning the matrix A into the identity matrix. Now we know that that can be done because A is an invertible matrix, so it can be row reduced to the identity matrix. So all of our attention is on the left-hand side of this augmented matrix. We're performing row operations with the intention of turning A into the identity matrix. Now what theorem 3.14 tells us, though, is at that same time, that same sequence of row operations is turning the identity matrix into the inverse matrix. So while all of our attention is on the left-hand side of this augmented matrix, while we're turning A into the identity matrix, we're also slowly transforming the right-hand side of our augmented matrix from the identity matrix into the inverse of A. So what appears here ultimately on the right side of this augmented matrix is the inverse of the matrix A. All right, now I think this will best be understood by looking at a couple of examples. Let's work the following problem. If it exists, find the inverse of the matrix A given here, this 3 by 3 matrix. Now what I want us to do is use our previous result. We're going to take the matrix A, we're going to augment it by the identity matrix of the same size, so namely a 3 by 3 identity matrix, and this is going to give us a matrix with 3 rows and 6 columns. We're going to concentrate on row reducing this left-hand side. We're going to row reduce that to the identity matrix, and we will slowly transform this right-hand side into the inverse. Now, this work can be a little bit tedious, and so what I'm going to do is just concentrate on the method and not so much on all the calculations that are involved. So let's go ahead and make use of the Linear Algebra toolkit to help us do some of our work. So I've taken the matrix A, I've entered it here, it's appearing here on the left, and we're augmenting that with an identity matrix, a 3x3 identity matrix. Now, we're really concentrating on this left half of this augmented matrix. We're row reducing it. And I can see I've got my leading 1 here, and I want to eliminate that -1 that's in row 3, column 1 in row 3. So I'm going to add 1 times the first row onto the third row. And that's going to update my matrix, and I've now got the leading 1 with the column of zeros below it. Now I'm going to use this leading 1 in row 2 to eliminate the 2 that's above it and the 1 that's below it. I'll do those in separate steps. So I'll do -2 times the second row added on to the first row. I've got that one eliminated. Now we'll do -1 times the second row added on to the third row. And now I've got that leading 1. It's the only non-zero element in its column. Now I have to create a leading 1 in this position, so I'm going to have to scale that third row by 1/2. And now that I've created the leading 1 in that position, I'll have to eliminate the 3 and the -2 that sit above it. So I'm going to do 2 times the third row added on to the first row. That eliminates that position. That's now a 0. And I'll do -3 times the third row added on to the second row. And we can now see that the left-hand side of this augmented matrix has been reduced to the identity. And that means that this 3x3 matrix that sits here on the right must be the inverse of the matrix A that we started with. So this is the Gauss-Jordan method for elimination to find the identity matrix. So this is this computation of the inverse via the elimination method. Now, I want to work one more problem with you just to show you that we can work this problem in other fields. So if it exists, let's find the inverse of the matrix A, now thought of as a matrix in Z2. Now we'll have to do this one at the document camera because I can't make the linear algebra toolkit operate in Z2 and do Z2 arithmetic. However, doing Z2 arithmetic is not that hard, so let's see how we could find the inverse of this matrix where we think of the elements as existing in the set Z2. So join me at the document camera for that. All right, welcome to the document cam. The problem that sits before us is to take this matrix A whose elements come from Z2 and find its inverse. And we're going to use this Gauss-Jordan method. So we're going to take our matrix A, we'll augment it by the identity matrix, and we're now going to imagine that all of the entries are in Z2 and all of our arithmetic, all of our elimination will be done relative to Z2. But we can still use this Gauss-Jordan method and work out the inverse for this matrix A. So we're just going to do elementary row operations to turn this into the identity matrix here on the left, and the inverse should appear on the right. So let's go ahead and think about what our first operations are going to be. We know that we want this leading 1 here to be the only non-zero entry in its column, and so we're going to use this 1 to eliminate the ones that sit below it. And because we're working in Z2, this is very easy to do. We can simply add row 1 onto row 2 and row 3. So we can simply scale row 1 by a factor of 1 and add that onto row 2. And scale row 1 by a factor of 1 and add that on to row 3. All right, row 1 is not changing. Row 2 is going to change by adding the addition of the element of row 1. So 1 and 1 are going to give me a 0. That's what we wanted. The 0 and the 1 produce a 1. 0 and 1 produce a 1. 1 and 0 gives me a 1. 0 and 1 gives a 1. 0 and 0 gives a 0. All right. Now we're going to do the same thing. We're going to take row 1 and tack it onto row 3. So the 1 and the 1 gives me a 0. 0 and 0 gives a 0. 0 and 1 gives a 1. A 1. A 0. And a 1. Okay, now let's see where we are. We scan down row 2. We come across a leading 1. And we notice that it's already by itself in its column. So that one's fine. Now we scan down row 3, we find this leading entry, it's a 1, and we want to eliminate the 1 that sits above it in row 2. And again, using Z2 arithmetic, this is easy. We just simply take 1 times, in this case, row 3, and add that on to row 2. Okay, row 3 is not changing. Now I'm going to see the effect on row 2. I'm adding 0 onto 0 gives me a 0. 0 onto 1 gives me a 1. 1 onto 1 gives the 0. 1 onto 1 gives a 0. 0 onto 1 gives a 1. 1 gives a 1. And then row 1 is not changing. Okay, we've now produced the identity matrix on this side. And according to the Gauss-Jordan method, that should be the inverse sitting on that side. Now, it might be helpful to see if this actually works. So bear with me here. Let's take the matrix A and let's multiply, let's say on the right, by this inverse matrix. Let's see if this works. We'll test this. Okay, let's do this, some dot products here. Remember, everything is still in the Z2 sense. So that's 1 plus 0 plus 0, that's a 1. 0 plus 0 plus 0. 0 plus 0 plus 0. So far, so good. Let's go on to the second row here. 1 plus 0 plus 1. Well, 1 plus 1 is 0 in Z2. 0, 1 plus 1 plus 0, so that's a 1. 0, 1, 1. 1 plus 1 is 0. 1 plus 0 plus 1. 1 plus 1 is 0. 0, 0, 0. And finally, 0 plus 0 plus 1 is 1. And we can see that it's doing what an inverse should do. Okay, so this just goes to show you that this Gauss-Jordan procedure can be extended even into like elements from Z2 or in general ZP, where P is a prime. Okay, so I hope that was interesting to you. That brings an end to section 3.3. We've done a lot in section 3.3. It is chock full of lots of interesting facts and lots of interesting things. So I hope you've enjoyed this presentation.